What specific problem does the KnowSelf method aim to solve in the context of existing agent learning methods?
The KnowSelf method aims to solve the problem of agentic knowledgeable, which refers to the agent's ability to recognize whether it can provide the correct next action based on the current environmental situation. Existing agent learning methods often lead to unconscious pattern fitting processes, resulting in inefficiencies and brittleness in planning behaviors. KnowSelf addresses this by enabling agents to selectively incorporate knowledge based on their situational awareness, allowing them to self-explore and classify situations into fast thinking, slow thinking, and knowledgeable thinking. This selective mechanism reduces excessive reflection and knowledge injection, ultimately enhancing decision-making efficiency and performance in dynamic environments. The method's effectiveness is demonstrated through superior performance in experimental evaluations compared to various baselines, highlighting its contribution to improving agent planning capabilities.
How does the proposed KnowSelf algorithm work? Illustrate the step-by-step process involved in its implementation.
The KnowSelf algorithm operates through a structured, data-driven approach to enhance agentic knowledgeable capabilities in language models. First, it classifies the agent's situations into three categories: fast thinking, slow thinking, and knowledgeable thinking, based on the agent's ability to predict the correct action. Next, it constructs a training dataset by augmenting historical action pairs with special tokens that indicate the type of thinking involved. The training process consists of two stages. Initially, the agent undergoes supervised fine-tuning to learn basic planning patterns, followed by a second stage utilizing a reinforcement policy optimization (RPO) loss to refine its decision-making abilities. During inference, the agent generates actions based on its situational awareness, selectively incorporating knowledge when necessary, thus allowing it to adapt its strategies dynamically based on the environment.
Can you provide a simple yet illustrative example to demonstrate the inner workings of KnowSelf, detailing how it decides between fast thinking, slow thinking, and knowledgeable thinking?
An illustrative example of KnowSelf's decision-making process can be seen in a scenario where an agent is tasked with navigating a room to pick up an object. If the agent quickly identifies the correct action to take, e.g., move to the object, it engages in fast thinking where the predicted action matches the correct action directly. However, if the agent initially predicts an incorrect action, e.g., move away from the object, but then reflects and realizes the mistake, it enters slow thinking. Here, the agent rethinks and corrects its action to the right one after some deliberation. In cases where the agent cannot determine the correct action even after reflection, it resorts to knowledgeable thinking. For instance, if it predicts an incorrect action and cannot correct it, it will invoke external knowledge, e.g., consult a map to guide its next steps. This structured approach allows KnowSelf to adaptively select the appropriate cognitive strategy based on the situation at hand, enhancing its planning capabilities.
What are the theoretical or practical benefits of using the KnowSelf method over traditional agent learning methods, particularly regarding efficiency and decision-making accuracy?
The KnowSelf method offers significant theoretical and practical benefits over traditional agent learning methods by enhancing decision-making efficiency and accuracy. Firstly, it enables agents to possess agentic knowledgeable capabilities, allowing them to assess their own cognitive states and selectively incorporate knowledge based on the current situation, which contrasts with traditional methods that often rely on rote memorization and pattern fitting. This selective knowledge introduction reduces unnecessary trial and error processes, thereby lowering inference costs and improving efficiency. Additionally, KnowSelf's two-stage training process, which includes supervised fine-tuning followed by reinforcement learning, equips agents with a more robust planning capability, leading to superior performance on tasks with minimal reflection and knowledge compared to various baselines. Experimental results demonstrate that KnowSelf achieves optimal performance with a lower knowledge rate, indicating that it can effectively enhance decision-making accuracy while minimizing the need for excessive knowledge injection. Overall, KnowSelf addresses the limitations of traditional methods by fostering a more adaptive and context-aware decision-making process in agents.
How is the performance of KnowSelf validated in the experiments? Describe the datasets used, metrics for evaluation, and the benchmarks against which it was tested.
The performance of KnowSelf is validated through experiments on two real-world simulated planning datasets, ALF World and WebShop. ALF World involves household tasks requiring navigation and object manipulation, while WebShop simulates an online shopping environment with dense rewards. The evaluation metric used for both datasets is average reward, which measures the completion level of tasks. KnowSelf is compared against various baselines, including general agent planning methods like React, trial and error methods such as reflection and ETO, and knowledge-augmented methods like Expel, KnowAgent, and WKM, as well as GPT-4o as a strong upper-bound baseline. The results demonstrate that KnowSelf consistently outperforms these baselines, achieving superior performance with minimal reflection and knowledge, thus validating its effectiveness.
What limitations or potential drawbacks does the KnowSelf approach have based on the experimental findings or underlying assumptions?
The KnowSelf approach, while innovative, has notable limitations and potential drawbacks, as highlighted in the experimental findings. Firstly, the performance of KnowSelf is contingent on the model's capability. Weaker models may suffer from excessive knowledge injection, which can lead to counterproductive effects, as seen in the comparison with baselines where models like Gemma 2B performed poorly with high knowledge rates. Additionally, the reliance on a heuristic criterion for situation classification may not capture the full complexity of dynamic environments, potentially leading to misjudgments in the agent's situational awareness. Furthermore, the training process, which involves a two-stage method, may not generalize well across all tasks, as evidenced by the overfitting observed in baselines when external knowledge is introduced. Lastly, the findings suggest that merely prompting models is insufficient for achieving true agentic knowledgeable self-awareness, indicating that further advancements in data, training strategies, and model architecture are necessary to fully realize the potential of this approach.